We will start by looking for evidence of feedbacks in the Earth system, which is the main purpose of this entire course, especially focusing on what are relevant right now in the climate state that we are in and where we are headed. We have seen various versions of this, especially the Brotherton diagram, which had put human beings on the side as external forces, but just to remind ourselves, we have the input from the sun, which is being used to drive the processes in the hydrosphere, atmosphere, cryosphere, and the biosphere, and so on. Without going into all the details of the processes, remember that we are most concerned with human influences. I like this compared to the Brotherton because this human influence is put right here in the middle with our energy consumption by various activities, including windmills, which is our effort to mitigate our own impacts. And it also shows the atmospheric chemistry, which is what and the biosphere, which are kind of the processes, especially like soil biosphere interaction and so on, that we want to include in the climate sensitivity and the Earth system feedbacks. Let's start with the land biosphere processes then in terms of feedbacks. To define critical key terms, evapotranspiration is one. I think everybody is aware of what it means, but in case you are, no big deal. Evaporation, you know what it is. It's dependent on the water vapor pressure difference of the water body from which the water is being lifted and the atmosphere above, and its exponential dependence on temperature we already talked about. It also has a dependence on wind and some exchange coefficients, stability parameters. Transpiration is essentially shown here as a schematic from the site, where evaporation is directly from the water bodies, whereas transpiration is any water that is being lost to the atmosphere by the mediation of vegetation. Okay, so trees and grasses. So they lift the water, they open the leaves for some capturing CO2 for photosynthesis, and there is a loss of water vapor there, which is also evaporation essentially. So it's called it's transpiration, like our sweating. So it's evapotranspiration, and it's a key parameter that actually determines the amount of photosynthesis happens, the amount of carbon that's captured, and so on. And we will look at that a little bit more detail later on. And just to put a framework for the feedbacks, we will already show this as an indicator of the complications of the feedbacks involved and why it could be very difficult to directly estimate from the observations, and how hard it will be to evaluate in the models as well. Because feedbacks always have to be done by saying, if this process was not turned on, what would be the change, let's say, in temperature or the CO2 flux, and what is the flux when you actually turn on the feedback. In the model, it's easy to turn them on and off if the models have all the details. So we will look at those kinds of issues. But putting vegetation here in the middle, you have loops like this, where at higher latitudes you have snow masking. For example, the trees in temperate and boreal forests have to deal with a lot of snow and how to survive through that. And you have canopy darkness processes, so you can have positive and negative feedbacks affecting the albedo. So you have cooling because of snow reflection or increasing by changing the vegetation processes, and it affects the radiation and the vegetation back. I'm not going to go through each of the signs here. I'm just trying to show it as an example of complications. Canopy roughness, which affects the airflow, boundary layer height, convergence, etc., that we will look at. Vertical mixing of either pollutants, flux from the atmosphere, so from the land, so energy exchanges and so on, which affects evapotranspiration. There is also an impact on leaf area for gas exchange, which is important. Bowen ratio, which is the ratio of latent to sensible heat, which is critical for many of the precipitation processes, and surface heat loss, so surface temperature, and of course cloudiness and precipitation. So you can see that this is shown as net positive feedback here, because typically what you do is you multiply all the feedbacks in this loop, so you have 3 positives and 3 negatives. So it should be there is 2 positives and 2 negatives here, so this is positive, this is a positive and a negative, so this will be net negative, and here you have 4 positives and 1 negative, so you have a net negative. So it's complicated, but we desperately need to know whether as a whole there will be positive feedbacks or negative feedbacks. The most critical one is always the role of the soil moisture. This is a nice paper by Sonia Seneviratne, which looks at evaporative fraction and its maximum, which depends on runoff and other terms. So it's basically arguing for temperature ranges where the let's say the dryness of the soil and the wetness of the soil determines the maximum evaporation, or which can correspond to maximum vegetation growth, photosynthesis, and so on. So you can see that the soil moisture here is a limitation. So even if energy is available to pick up moisture from the soil, you can have limitations on evaporation because soil moisture is limited. Whereas if you go to wet soils where soil moisture content is in this range, then it depends on how much energy there is to cause evaporation or evapotranspiration. So here is a theta wilt where the it's called a wilting point. So the evapotranspiration here becomes soil moisture limited. So without evapotranspiration, you can basically think of plants being limited in their photosynthesis, carbon capture. In agriculture, it will be crop yield loss, crop stress, and so on. And this is theta critical, where the critical soil moisture content, where evaporation either goes into energy limited or soil moisture limited. So it's kind of a nice heuristic argument to show that the controls on evapotranspiration is going to depend on specifics of the soil types, the season, for example, irrigation, which is going to control soil wetness, essentially to avoid the wilting, for example, and so on. And what we are interested in, of course, here, evapotranspiration corresponds to energy exchange between the land biosphere and the atmosphere. So we are looking for that biophysical and biogeochemical feedbacks, because associated with these there will also be carbon fluxes, right? So it's not just evaporation and transpiration, it's also going to be carbon fluxes. So we have to somehow combine those. In the models it's done, but it used to be done in a very simple way. Now it's getting more sophisticated, so we will see those kinds of details as well.